All right, guys, so there's actually not much that's going to be new today. We are going to use all of our knowledge from the previous lessons to kind of combine this into a full analysis of the function. We're also going to draw on some previous knowledge from advanced functions to identify x-intercepts and y-intercepts and stuff like that. So there's kind of some steps for you guys here that you can use to analyze a function. In advanced functions, we did a lot of sketching of polynomials and things like that. And a lot of times the question comes up like, when I know where my x-intercepts are, how do I know how high those mountains go or how low those valleys go? Well, now with our information with calculus, because we can determine local maxes and local mins with the first derivative, we actually know how high and how low the way the function goes in between the x-intercepts. So that's part of what we're going to add to our knowledge. We're also going to be able to see the intervals of concavity, so decide where the function kind of changes concavity, so points of inflection. And we're going to apply our curve sketching, first derivative, second derivative, stuff like that, to rational functions as well. Okay, so just kind of expanding on some of the stuff that we did in advanced functions and then utilizing derivatives to get more information from the function. Okay, so the very first thing that we're going to do when we analyze any function is determine any restrictions that could be in the domain, and if there's any horizontal asymptotes, vertical asymptotes, or undefined points, we want to indicate that. So basically, mostly that just refers to rational functions, because basic polynomial functions like this, they don't have any restrictions in their domain. They just go on from negative infinity to positive infinity. So the first one for this, there's going to be no restrictions and no asymptotes. The second thing that we're going to do is we're going to determine the intercepts, so x and y intercepts of the graph. So what we're interested in is to get x-intercepts, where is this function equal to 0? So when we have a cubic like this, we have two options. If it's a 4-term cubic, we can test to see if we can factor by grouping. I don't think these groups are similar enough to factor by grouping here. We're not going to get the same brackets. So the other option for factoring a cubic is to find possible factors, test them, and use synthetic division. Okay, so we'll do a little recap of this. When we have a cubic or degree that's higher than 2, and the leading coefficient is not 1, we will find factors of the constant. And that would be plus minus 1 and plus minus 2. And we will also find factors of the leading coefficient. So that will be plus minus 1 and plus minus 3. And our possible factors, the ones that we kind of test in the polynomial, are all combinations of factors of the constant over factors of the leading coefficient. Okay, so 1 over 1, that's going to give us plus minus 1. We'll do 2 over 1, so that will give us plus minus 2. 1 over 3, that gives us the option of plus minus 1/3, and 2 over 3. Okay, try not to write too big on here. There is a bunch of space on the next page, but we don't want to take up a lot of space with this. Okay, then we're going to do some tests. So we're going to test in our polynomial until we get 0. So for instance, we will start and work our way. I don't usually like to plug in the fractions. Usually you'll get at least one whole number. That's not guaranteed, but usually you will. I like to test the whole numbers first. So here we'll get 3 minus 2 minus 7 minus 2. That gives us what? Negative 8? No. Yes. So therefore, x minus 1 is not a factor. Okay, let's try f at negative 1. Maybe that will work. We'll get negative 3 minus 2 plus 7 minus 2. Does this work? Yeah. Okay, that gives us 0. Therefore, we can stop there. X plus 1 is a factor. Okay, so we are going to apply synthetic division now. Use this value that you plugged into your function. Okay, so the factor is x plus 1, but we use minus 1 over here, and then you're going to list your coefficients in descending order as far as like the exponent on the x's. Remember to put any 0 placeholders if there's any value missing. So if I didn't have an x term, for instance, I would make sure I put a 0 placeholder there. Okay, so we drop the first term. I'm not going to do that. I'm going to go through this part slowly, and then if we do any more synthetic divisions, I'm going to go quicker, okay? Then multiply. So -1 times 3, -3, add in this column. So we get -5. Multiply through again by -1, we get +5. Add, we get -2. And then multiply one more time through by -1, we get +2. If I've calculated this test correctly, I should expect to get a remainder of 0 out. If I don't get a remainder of 0 out, that thing is either not a factor or I've done my synthetic division incorrectly, right? We found the factor ourselves, so we know it should have a remainder of 0. Okay, so work your way right to left. Remainder, constant, x term, x squared term. Okay, we're going to continue up here with our factoring. So do not forget the factor that you divided by. That's the first factor there, x plus 1. And then we're going to create a trinomial from this, so 3x squared minus 5x minus 2. And then you're just going to factor that quadratic. So I think we get 3x plus 1. And x minus 2 here. Okay, so that should give us x-intercepts. We have x-intercepts at -1, -1/3, and +2. Y-intercept, nice and easy. You are just subbing in 0 for x in your original function. If it's a polynomial just in standard form, it's just the c value, right? Because if we plug in 0 for all those x's, all we'll be left with is -2. So our y-intercept is the point 0, -2. Oops. Yeah. Okay, so that's just kind of our side work for number 1. Okay, this is kind of what we did in advanced functions. So this is just kind of a recap of how we find those intercepts. And then we kind of just used like end behavior, and we used like degree to kind of help us make some decisions and graph from there. Now with calculus, we have a lot more information about like where the turning points are, where the points of inflection are. So we're going to keep analyzing this function. Anita?
If there's no like coefficient, would you just use the factors?
If the leading coefficient is equal to 1, you'll just use the factors of the constant. Yeah. Good question. Okay, let's go on to part 3 here. So part 3, we're going to determine critical numbers, and that is where the first derivative equals 0. Okay, so you guys have been working with this for a while. So f prime at x equals 9x squared minus 4x minus 7. And we set that equal to 0. So our options here are we could try to find two things that multiply to negative 63 and add to negative 4. I don't know that we're going to find that. Really, like the factors are like 9 and 7, which is not going to add to negative 4. We could do like 3 and 21. That's not adding to negative 4. There's not a lot else that we can do there. So what you're going to do is if you can't factor something and it's a quadratic, we're going to use quadratic formula. Okay? It is possible that your quadratic might not have any roots, so you can always test in the discriminant first just to make a quick decision. So is b squared minus 4ac negative or is it positive? If it's negative, you don't have any critical numbers for that part or any roots or whatever. Okay, so I'm going to plug this into quadratic formula. It's negative b plus minus b squared minus 4 times a times c over 2a. Okay, so take a second and calculate that out. I don't need to see all the simplification work. You just find your x's and we'll go from there. Okay, anyone have our x's? No one has them? Negative 0.69. Anyone else? Can someone confirm that for us?
I got that.
How many decimal places do we want?
I think 2 decimal places is probably decent. We're going to be graphing it, so there's not that close that we can get to like being super accurate beyond like 2 decimal places for a graph. So 1.13, and was it negative 0.69? Okay, great. So these guys are critical numbers. We'll just take an extra second here and find the critical points. So you're going to evaluate f at 1.13 and f at negative 0.69 so that we have the y coordinates of those critical points. Basically, the steps are find where the original function equals 0, find where the first derivative equals 0, find where the second derivative equals 0, and then create a chart. So find where everything's equal to 0, basically. So yes, the answer to your question is yes. Okay, what did we get here? Anyone?
Negative 8.14. And I got 0.89.
Okay, did everybody else get these numbers? Let's just double check here. Oh, here we go. It's right here. Lovely. Looks good. Whoops. Sorry, I lost my spot. There we go. Okay, so our critical points are 1.13, negative 8.14, and negative 0.69, 0.89. Box those up. We're going to need those later. Okay, so we found our critical points. We are also going to analyze where the second derivative equals 0 to find possible changes in concavity or possible points of inflection. So lots of room on the next page if you guys want to flip, if you need to flip over. I am going to find f prime prime at x. Okay, so working from this equation here, we're going to find the derivative of that. And we're interested in where this equals 0. This one's a little bit easier to solve, so that's nice. Okay, and then you're going to evaluate f at 4.5 so that we have the actual point. So, oh wait, did I do something wrong? Oh, 2 over 9. Good thing I checked. Oops. There we go. Sorry. So we'll keep it maybe as like 2 over 9 when you plug it in. Okay, when we go to graph, we will need to know kind of the approximate value of this, so we can do like 0.22. And what do we get for this when we plug it into the function? More decimals? No? What is it? 6.2? Okay. Oh, okay. You plugged in 2 over 9, Anita?
Yeah.
Yeah, okay. So we have a possible point of inflection at about 0.22, negative 3.62. Essay?
If we check it using the secondary test, is it
We're going to check everything all together right after this. So we're just going to kind of identify those, and then we're going to classify them like once we do the test, and we're going to do it all in one chart. Okay, so we've put together some of our earlier information, finding critical numbers. Now we've put together our information about the second derivative. In our previous lessons, we did these as separate charts. Now that we have all of this information, we're going to kind of put it together and then create a chart that kind of shows us the information all together. So every vertical asymptote, critical number, and possible point of inflection, so the x-coordinate of that is going to be contained in our chart. The x-intercepts don't need to be contained in the chart, right? Those are just information for when we graph. So I'm going to do 5 and 6 together here. We're going to create the sign chart, and we're going to put all vertical asymptotes, all critical numbers, and all possible x values of our points of inflection in there. Okay? So 5 and 6. I'm going to create a nice chart here. So we have 2 critical numbers and we have 1 point of inflection. So we want 3 lines at least in here. And then I always put 2 on the ends for negative infinity and positive infinity. Okay, and we're actually going to test the second derivative and the first derivative for each of these things. So I'm interested in f prime prime at x, f prime at x, and then we'll make some conclusions about f at x in those intervals. So lowest number here is negative 0.69. And then we've got 0.22 and 1.13. Choose some test values that will work for those intervals. And And we're going to take a couple minutes and we're going to plug each of these into the second derivative so we can actually see it right here. That one shouldn't be too bad. So -2 in here, that's going to give us negative. 0 in here will give us negative. 1 in here will give us a positive. And 2 in here will give us positive. And then we're going to take each of those test values, we're going to plug them into the first derivative. So using this equation here, 9x squared minus 4x minus 7. So this one we use 18x minus 4. This one we use 9x squared. You don't have to write this, but I just need to, I don't want to keep scrolling back and forth. This one we're going to use the first derivative function, so plug each of your test values in there. Okay, I'll give you a couple seconds to do that. We'll pause. Okay, what did you guys get for each of these sections here? Positive, negative makes sense, negative, and positive. Okay, so are we good? Did everyone else get that? Yep? Okay, good. So we're going to make a conclusion in each of these intervals about concave up versus concave down, and then also increasing and decreasing. So in this interval here, because the second derivative is negative, we are concave down. And because the first derivative is positive, what does that tell us about f at x? Increasing. So we are concave down and increasing. That means that the shape of that section is kind of like that. Okay, in this next section, we're still concave down, but now we have changed from increasing to decreasing. So we have something that looks kind of like this now. So what does this tell us about negative 0.69? It is a local max point. Great. Next section here, second derivative is positive. That means we're concave up. And first derivative is still negative, so we are decreasing there. So I want to draw something that is concave up and decreasing as we go from left to right. Looks kind of like this. Okay, notice here, so what is 0.22? What conclusion can we make about that? So we don't change from increasing to decreasing or decreasing to increasing. It can't be a local min or local max, but we do change concavity there. And where we change concavity is a point of inflection. Okay, remember this point up here was a possible point of inflection. So that in fact is a point of inflection. And then here we're concave up and increasing. So something like this. What does that tell us about 1.13? Local min. Okay, so I'll scroll down in 1 second. Number 6 also asks us identify intervals of increase, decrease, and intervals of concavity. So we're just going to take a second and list those out. So where I'm looking for increasing, I'm looking along these intervals here. So we are increasing in this interval and also in this interval. So we would want to say from negative infinity to negative 0.69, and then also from 1.13 to infinity. Decreasing, again, we're still looking at the first derivative here. I don't need to exclude a point of inflection from a decreasing interval if it's decreasing along this whole thing. I do need to exclude a vertical asymptote if we have a vertical asymptote, but points of inflections don't need to be excluded. So we can just say from 0.69 to 1.13. Okay, and then for your intervals of concavity, we'll say concave up. We're now interested in this column where it's positive. This is positive all the way from this point of inflection to infinity. Again, I don't need to exclude critical numbers from this. I only need to exclude areas where the function is like undefined, like a vertical asymptote. So that is an area that's concave up from 0.22 to infinity. Okay, and then the last one, this section right here, that's the area where we're concave down. And that is from negative infinity to 0.22. Okay, again, I don't need to exclude the critical number from that. That's not where the second derivative equals 0. So we can include a critical number there.
Why do you need to do it for the first one?
Pardon?
Like, why do you include both for the first? Oh, no, right. Okay, so 0.22 is this critical number, so it's allowed to be included in intervals.
0.22 is a point of inflection. Right.
If that wasn't asymptote,
Then we would exclude it from both intervals.
so would it be
Increase and decrease and concavity.
so x is less than 0.22?
Yeah, so you would essentially just have to break up this interval in between here. Okay, part 7 wants us to just do like a final list of like local maxes, local mins, points of inflection, just to kind of write it out. So we kind of did that up here when we classified, but we have a local max at that negative, what was it, 0.69, and what was our y coordinate there? 0.89? Okay, perfect. We have a local min at the other point, so that was 1.13 and negative 8.14. So I mean, you can imagine these questions, I can basically test like just about everything that we've done so far, right? So this is a very good like culminating question. And we have a point of inflection at that 0.22, and what was the y coordinate? Negative 3.62. Okay, last step, all that we need to do now is graph all of this. So you are going to graph all your intercepts, x and y. If you have vertical and horizontal asymptotes, of course, include those with a dotted line, label them. We'll plot local maxes, we'll plot points of inflection, and then decide on what our graph looks like using our intervals of increase, decrease, and concavity. Okay, so let's plot here. X-intercepts, let's slide back up here. Our x-intercepts are -1, 2, and -1/3. So graph those. Y-intercept was -2. Is that right? Okay. And then you're going to plot your local max and local min. I'm just going to zoom out here so that I can see them. There we go. -0.69, 0.89. I'll do the local maxes and local min in pink. Okay, something like that. And then 1.13, -8.14. Okay, and then point of inflection, I'll do that one in green, 0.22, -3.62. Okay. So with all of this information, and we also know some information about like increasing, decreasing, and changes in concavity. At this point, this green point here, we're changing concavity. Up to that point, we're concave down. So our intervals of increase tell us that until this point right here, where we have a local max, we are concave down and increasing. Then we change to decreasing from there. And then there's a change in concavity. So still decreasing, but now we're concave up. And again, local min, we hit a local min. Now we're increasing, but we're still concave up. So the graph looks something like this. Okay, if you want, you can, I don't need you to label the points, but I'll just label them just so that you guys can kind of see where each thing was that we found. All right, so that is your essentially like full analysis of this function. We found everything there is to find about this as far as characteristics, and that helps us get like a really good full sketch of the function. Okay? All right, we're going to do a rational function. Same process. I'm going to take this one maybe like a little bit faster with like the derivative parts and stuff like that. So let's take a look. Okay, you need to identify any restrictions in the domain, vertical asymptotes, horizontal asymptotes, things like that. This is a rational function, so we do have vertical and horizontal asymptotes. The vertical asymptotes are the restrictions in the domain. So what are our vertical asymptotes here? -1 and +4. Horizontal asymptote? Oops, sorry. How do you know that, Grayston? Yeah, so this is degree 2. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is just at y = 0. Okay, so in your domain, x should not be equal to -1 and 4. Okay, so just keep that in mind as like restricted values of your domain. It's just essentially the vertical asymptotes. Okay, so when we create our chart at the end of this, -1 and 4 are going to be in our chart. Okay, second part, I want to know where this function is equal to 0 to find the x-intercepts to start. Right, so is 1 ever going to be equal to 0? So this actually will never be equal to 0, so therefore there's no x-intercepts for this one. Why does this make sense based on our information above? Essay? Yes, so there are no x-intercepts, but we can evaluate y-intercepts. We'll just evaluate g at 0. We'll get 1 times -4 on the bottom, so that will give us -1/4. It is right now. So we are at the point 0, -0.25 for our y-intercept. Okay, so that was, oh, that's the second step of the steps above. Okay, next step after this, we're going to analyze the first and second derivatives. So that's steps 3 and 4. Identify critical points, identify points of inflection. So let's start with the first derivative. Derivative of the top times the bottom. You know what? I'm actually going to, just so that we know what this is expanded, it'll be a little bit easier to take the derivative. That is the bottom expanded. So when we do like the bottom here, I'm just going to leave this rather than doing product rule for the second part. Minus the top times the derivative of the bottom. That's just 2x minus 3. So taking the derivative of this guy. And then the bottom we can just leave in factored form. So it's just the bottom squared. And we're interested in where this equals 0. So Okay, so this equals 0. We talked about this in our rational functions stuff yesterday. This equals 0 where the numerator equals 0. So in order to find where this is equal to 0, we just need to find where 2x minus 3 equals 0. Okay, and that will happen when we have 3 over 2, okay, or 1.5. And then you're just going to evaluate g at 1.5 so that we have the point. So plug that into your original function. You guys got negative 0.16? Lovely. So we have a critical point. No, that's only for points of inflection. This is a critical point. Okay, so we found our critical point using the first derivative. Now we're going to use the second derivative, find any possible points of inflection. I think it will be a little bit easier if we take, so I'm just going to put, instead of this, I'm going to put the expanded form of x plus 1, x minus 4, because I think the derivative will be a bit easier. And I'm also going to put that negative in, just because I don't want to have to do like product rule or anything like that. So we'll just do it like the simplified version, kind of to make our lives a bit easier. Okay, so second derivative, we are going to do derivative of the top times the bottom minus the top times the derivative of the bottom. So this is going to be chain rule. So apply power rule on the outside, and then you need to multiply by the derivative of the inside, which is 2x minus 3. And square the bottom. Okay, so I'm going to take out a common factor of negative 2 here. So I'm going to take out the 2 here, and maybe I'll take the negative out of this just because we have another 2x minus 3 there. And I will also take out one of these from each term. So taking out a negative 2 and one of the x squared minus 3x's minus 4's. We should be left with one of them in this first term. So just x squared minus 3x minus 4 minus, so I took out this 2 and I took out a negative from here. So it will be minus 2x minus 3 times another 2x minus 3 over here. Okay, so I'm going to just simplify this a little bit. We'll cancel one of those out with the bottom. And then we're just going to FOIL this guy in here, distribute the negative in there as well. We're almost there. So I'm just going to kind of gather this all together. We're going to get an x squared minus a 4x squared. That will give us a negative 3x squared. We will get a negative 3 plus 12x, negative 3x plus 12x. I think that's right. Correct me if I'm wrong. Gives us positive 9x. And then we're going to get a negative 9 and a negative 4. That will give us negative 13. Okay, so we are interested, again, when we're dealing with a rational function, this is going to be equal to 0 where the numerator equals 0. So we have some options. We can try to find something that multiplies to 39 and adds to 9. 3 and 13 are kind of the only combinations that we have there for 39. And I don't think that's going to happen for us. So you're going to use quadratic formula here. Okay, where A equals -3, B equals 9, and C equals -13. So plugging into the quadratic formula. Okay, I'll give you guys a second to do that. Let's resume that. Sorry, we just forgot the negative there, so I'll erase that. Okay, so is anyone finding anything here as they try to enter this in? Sorry, with the -13? This discriminant is negative. So what does that tell us about roots for this function, at least on the top here? Okay. So b squared minus 4ac in this case is actually less than 0 or negative, therefore there's no roots for this one. That also tells us we have no possible points of inflection. Now that doesn't mean we don't change concavity because there's vertical asymptotes. We could definitely change concavity on opposite sides of vertical asymptotes. So there's no points of inflection, but there might be still intervals of concavity where we switch from up and down. Okay, so that part is done. Okay, we're in the home stretch. We're going to create the chart. Do 5 and 6 together here. So you are going to include critical points and vertical asymptotes here. We have 2 vertical asymptotes. They are -1 and 4, and we have 1 critical point. It's 1.5. Okay, obviously still good that we found the second derivative because we do need to test our test values in the second derivative still. So that whole step was not for no reason. Okay, choose some test values in between here. We'll do 3 and 6. Okay, so I'm going to give you guys a couple seconds. You're going to plug these first ones into the equation for the first derivative. Plug the other ones into your equation for the first derivative. Sorry, did I say first derivative last time? Second derivative and first derivative. Record whether you get positive or negative, and then we'll make some conclusions here. So I'm going to pause for a second while you guys fill that out. Okay. I trust that you guys can plug these in. So what you should get here is positive, negative, negative, positive. And then we should get positive, positive, negative, negative. Oh, sorry. And did I start my recording? Yeah, I did. Okay, so I think I'm more concerned about the deciding on conclusions here. So in this section, look at this for concavity, look at this for increasing, decreasing. So this is concave up, concave down, concave down, concave up. Okay, looking at the second derivative, the first column. Second column, we are increasing, increasing, decreasing, decreasing. And just as a reminder, these are vertical asymptotes here. So you can kind of just put those at the bottom just to remind yourself they're not local maxes or local mins or points of inflection. Okay, so concave up and increasing, here's what we look like. And then concave down and increasing. Concave down and decreasing. And we knew that 1.5 was a critical number, so what does that mean about 1.5? Local max. And concave up and decreasing, so we're looking at something like this. Okay, I don't necessarily need you to write out all the intervals of increase, decrease. If it helps you sketch it, you can. I think we can kind of see them here. Like I can see, obviously we're increasing along here and we're decreasing along here. So, I mean, if I ask you in the question specifically, write the intervals, then you can write them. But I think we can kind of look at the chart and see. So we'll just identify the local max, local min, points of inflection. All we have here is a local max at 1.15, and the y-coordinate was negative 0.16. Okay, and then our last thing is just a sketch. So don't forget your horizontal asymptote above. We didn't use it in the chart just because it's part of the range, not the domain. So graph your asymptotes to start. So -1 and 4. We also had a horizontal asymptote at y equals 0. We have a critical number at 1.5, negative 0.16. So I'm going to plot that. That's like something like this. Okay, and that's actually all the points that we have. The other areas, we just know concave up, concave down, increasing, decreasing. So from negative infinity to -1, we are increasing and concave up. Should look something like this. Okay, from -1 to 1.5, we are now concave down, but increasing, so probably something like this. Then we change, we're still concave down, but we change to decreasing after that. And from 4 to infinity, we are concave up and decreasing now. So, oh yeah, we should have graphed that. What was the y-intercept? Okay, so I probably have to just like adjust this a little bit. Thanks, Anita. Negative 0.25, so we should have that as well. So just make sure your graph goes through that point. Yeah. Oops, sorry. Okay, so there's our graph. That's it. That's what we've been working up to.